Welcome to lecture 17. In this lecture, we will look at clock synchronization in distributed real-time systems. So what happens is that in a distributed system, we have different clocks at each node. So that is why synchronization between them becomes difficult. And given that real-time systems are tied to the value of the clock that gets real time, not logical time, clock synchronization is even more important. So the system that we are looking at in this lecture would basically be a bunch of systems that are connected over the network, right? Over the internet, maybe. So this would be a distributed real time system. So, what are the users of clocks? Well, multiple things determining timeouts. For example, a job may be running, so we want to find out exactly when uh, the job will finish. So, well, I stand corrected. So, basically, what you could do is that if a job has started, and let's say the deadline is after t seconds, so what can be done is that we can set a clock whose timeout time is t seconds. So the job has not finished by that time, we declare a deadline miss. Time stamping, which means if an event is being sent, we can stamp the event with the current time. Ordering of actions, so if there are multiple actions which are concurrent, so we can order them. So we routinely see this happening in traffic lights, right, where one action happens after the other and there's a fixed order. So for example, we say that the green light will be on for 20 seconds, and then uh, after that we'll have amber and then red. So time stamping, needless to say, is important, as I have just mentioned. So it also helps the receiver get an idea of the age of the message, in the sense that how old is the message, and furthermore, what exactly needs to be done with the message. So the key idea is that if, let's say, if we have two clocks in a distributed system, so let's say, given the real time t, the value that this clock is actually showing could either be t or could be some other value, because clocks are typically not very accurate. So if we consider two clocks st and ct and look at the deviation between them, it should ideally be less than a threshold, right? And furthermore, what you expect is that, let's say, for any clock, if I just take the time derivative, right, the derivative with respect to time, that should ideally be equal to 1, right, in the sense that the clock is capturing wall clock time. But the point is, it may not be 1, it may slightly differ from 1. So what we do is we take the modulus of the difference, and this difference has to be bounded, so this has to be less than rho. So one more property, of course, other than these two, which is correctness, which means the deviation should be within bounds. And the second is that the drift, which is essentially a bound on the derivative, right, around 1. This also should be less than another threshold rho. So this third property that we desire in a good computer clock is monotonicity, which means that it should monotonically increase. So what we shall see in this chapter and the next one, there are algorithms to adjust clocks, but again, we should not be adjusting the clock such that, let's say, if there are two time instants where t is greater than t dash, this should always hold, in the sense whatever time the clock shows, you should have ct greater than ct dash, right? This means that under any circumstance, time should not be seen to flow backwards, right? So this should never happen. So this is the crucial property of monotonicity. So if monotonicity is violated, time will flow backwards. It can cause errors in a lot of software. A lot of software will run incorrectly, and you'll also have problems, or you may have problems such as the classic Y2K problem. So of course, a big deal was made out of it, and so this did invite a lot of software design activity. At the end, nothing great happened, but that is probably because so much of effort was put in. So the idea was that dates prior to the year 2000 were essentially stored as 75 for 1975, 98, 99, and so on. So a fear was that time may roll over in the sense that after 99, the time will roll over to 00 if this is the way that the year is stored, right? So basically, there was a need to actually change the logic of a lot of computer programs to basically after 1999 to make it 2000. So this did invite a lot of software design and redesign activity during that period in the late 90s, particularly. So this is known as the rollover problem. So another property is called chronoscopicity, which basically means that sudden large changes in the time value should not occur in the sense that the difference of the actual time should roughly be similar to the difference of the time that the clocks are showing, right? So basically, there should not be a major difference, right? So this is a property of chronoscopicity that so our clocks, as we shall see, they vary for two reasons. One is that, of course, as time progresses, the values that the clocks show that varies, right? That is a natural behavior. But many times we also correct clocks to account for drift and divergence and so on. So this is where the property of chronoscopicity becomes important, right? We want to vary our clocks gradually. We don't want to do major changes, sudden changes. So this is something that we would like to avoid. So if I talk about time stamping, so we have discussed this a few slides ago as well. So the key idea was that we want to take messages and stamp them with a time. So the entire system will know when the message was generated. So of course this is not the way that classical distributed systems work, because there we have causal ordering where what we do is that if let's say there is one event and that led to a message being sent to another thread or another process, right, or another program on a separate machine, and that led to event B. So there is a happens before relationship between event A and event B because a message was sent and subsequently received. So the real times, the clock times don't matter. This is known as causal ordering, right? Well, some events succeed some other events. So this would, needless to say, lead to a partial ordering of events, right? But again, in this case, if I just go back to this slide, we are not talking about causal ordering. We are talking about real clocks, right, which show real time. So we need to understand why in a large real-time system clocks will show some degree of divergence, or why they would tend to diverge, right? This is an important question. So it's very unlikely that any two clocks would of course run at the same speed. There would be some drift. So the difference in the reading, right? So difference in the reading of what the clock is showing and the actual time is the clock skew basically. And a skew, needless to say, as time passes by, the skew will increase with time. So over time, what will happen is any kind of an operation that relies on the value of the clock, like a timeout or a time stamping, these operations themselves will become quite meaningless, right? So they will lose their meaning. So this is why there is a need to periodically fix the values of these clocks. This is known as synchronization. In some settings, it's also known as resynchronization. So how do we control clock skew? We will discuss those approaches, but a few questions will be answered before that. What kind of clocks are used in a computer? Why and how much do they drift? And what is the notion of universal time? So, clocks in computers rely on the phenomenon of piezoelectricity. So, this was discovered by Pierre and Jacques Curie in 1880. So, the idea is that a quartz crystal will distort when a voltage is applied to the crystal. And then, when the voltage is removed, the quartz crystal will try to return back to its previous shape, to its original shape. And this would again generate a small potential difference, right? So, in a certain sense, a potential difference would cause a mechanical change, and then a mechanical change will cause a potential difference. So, there is a feedback loop over here. So, this is something that can work or that can be made to work as a classic oscillator in an electronic circuit. So the physical principle is that a quartz crystal will behave like an RLC circuit. It will have a very precise resonance frequency, the frequency at which it will oscillate, and it can be modeled, right? Any quartz crystal, right, which is used for the purposes of building a clock, can be modeled with the following equivalent circuit, right, where we will have C1 as a capacitor, inductor, and resistor, and of course another capacitor in parallel. So this circuit, right, uh, this quartz crystal over here, whose electronic analog is showing over here, was used to build the first quartz clock in 1921. So the key idea of this 1880 discovery of the piezoelectric effect was essentially that you squeeze a quartz crystal, it generates an electric field, and then you apply an electric field basically which is in tune with the field that has been generated, and then the crystal will bend. So this oscillatory process goes on. So you have a stable oscillator basically. So you have, if I would see some a stable wave, right? So in this case, actually, it's not a sine wave, but it's a square wave. So you have a stable clock, right? So which you can derive from a physical source, which is the quartz crystal. So 1929, so it took roughly 49 years to build the first quartz crystal based clock. So where it did have a resonator, which was shaped like a tuning fork, and it was tuned to vibrate at 32,768 hertz or 32 kilohertz. Quartz. The good thing about quartz crystals is that they are very accurate, right, at room temperature or even at the normal temperatures that we operate in. So the drift is roughly 6 parts per million. Okay, so for every million seconds, it may drift by 6 seconds. So what has been observed is that many watches gain or lose a half second per day, but you can also have a good resonator which will gain or lose 1 second in 10 years, right? So basically, even though the 6 ppm number is kind of representative of the average, you have, uh, you know, designs on both sides. And needless to say, the change in the frequency or the drift of the clock is dependent on several factors. One is, of course, the age of the clock, the ambient temperature, how hot or how cold it is, and the level of acceleration. So, what are these factors that affect the frequency of a quartz oscillator? So, some I just discussed. Another important one is the angle at which the quartz is cut. So, this is more of a manufacturing level thing, where with respect to the principal crystallographic axis, how exactly was the quartz crystal cut? So, even its design has a say with regards to its target or final frequency. We've already talked about temperature and size. So here is, a photograph that shows two real watches. So basically, both were synchronized on September 18th, 2011, at exactly time. At this point, they were showing exactly the same time, which was 8 a.m. But after that, they drifted. So from September 18th to October 23, which is 1 month and 5 days, right? Just note the dates: September 18th, 2011, October 23, 2011. So there was a skew was recorded of 84 seconds and 108 seconds, right? So basically this did change, but mind you, this is just an example. It has nothing to say about the companies that manufacture these watches, and so this is by no means either a positive or a negative endorsement of the watch companies, because over the last 10-15 years, right, so this particular information is dated, but over the last 10 or 15 years, watches have become incredibly accurate, and many watches maybe lose at best a few seconds in a year, but otherwise watches today are super accurate. right? So, between 2011 and 2022, there's a big difference. So, there is a notion of a universal time, the UTC time, right? And so, this is the time that is maintained in a Paris clock. So, ideally speaking, any clock, uh, with respect to the UTC time, it should ideally be the same. So, this should just be a 45-degree line. If this is not the case, and the derivative of this line is not 1, then of course this signifies or this indicates a drift. Say the clock is slow, it would skew in one direction. If the clock is fast, it will skew in another direction, right? So basically, the perfect clock will have a dc by dt of 1. A slow will have a dc by dt which is less than 1, and a faster one will have a dc by dt which is more than 1. So, as I said, the typical drift is roughly between 6 to 10 parts per million, right? And so the manufacturer specs will provide the drift rate. So the maximum drift between any two clocks, right? So this is the drift rate, of course, with respect to UTC, but between any two clocks will be 2 rho delta t seconds. So to guarantee that two clocks will never differ by small delta seconds, we need to resynchronize the clock every delta by 2 rho seconds such that at the synchronization points, their times become the same. Then there is a small amount of limited drift, and again they uh, become the same, right? So we ensure that the maximum drift that happens in a period is bounded. So an important problem is that we need an effective solution for distributed real-time systems to ensure that all the clocks in a system agree on the same value or show the same value. So as I have said, the agreed time from different, the agreed time is UTC for all the machines in the world. This is known as a universal coordinated time. So the UTC is like this. This is a new prime time standard by which the world regulates its clocks and times. So there are many official internet time servers that provide the UTC time, and then of course you stay in a certain time zone. You know your offset with respect to UTC. Then you can set your clocks. But of course, the point is that many a time we need extremely accurate time precision. And for that, there is a different method that actually relies on satellites, where the satellites provide a time base, which is also the UTC time. And so this mechanism uses GPS, which we will discuss next. So the baseline UTC time, which is basically the baseline to which we need to synchronize all of our clocks, this is maintained in Paris, as we have discussed. So it's essentially the average of 70 atomic clocks located at laboratories around the world. All right. So this is the UTC time, and UTC signals can be obtained through one of the mechanisms other than internet time servers. Is to use GPS or global positioning system receivers and specialized radio stations. Let us look at the types of clock synchronization mechanisms. So we can have external clock synchronization where all the clocks are synchronized with respect to a clock which is external to the system. So this is normally what happens in regular desktop and laptop based systems. So which is also the case with the laptop that I'm currently using to record this video. So what happens is that we set up a time server. The job of the time server is to provide the exact time. So your mobile phones also work using such principles. Then you can have internal clock synchronization, I'm sorry, where all the clocks are synchronized with respect to some sort of a clock, which is an internal time base in the sense it is internal to the system. So the system in this case could be a desktop, or the system in this case could be a set of computers, with one of them being the time base. So the key idea is that if I were to synchronize it externally, then let's say if this is the UTC time source and this is the clock of the ith node, we would want the deviation to be bounded. If it is internal, in the sense, there is no absolute truth, in the sense there is no external time base, then for all pairs of clocks, we would like the difference to be bounded, which is to be less than capital delta. So external clock synchronization, as I have shown, there is an NTP protocol, network time protocol. So using this protocol, many nodes synchronize with a master clock. So this is how this synchronization happens. And for internal, of course, another protocol needs to be followed. So the pros and cons are this is easy to implement, zero communication overhead. But the point is, it is kind of expensive to have these GPS receivers at each node, which is why sometimes internal clock synchronization is preferred. So let us now come to GPS. So of course there are different ways. One is the network time protocol idea that I mentioned, and the other is that if I want to find my position as well as the exact time, so I can use the GPS system. So what happens is that there are multiple orbiting navigational satellites. So all of these satellites have atomic clocks. So it is assumed that all of them provide the exact time, provide the exact UTC time. And also they have an exact idea of their position. So both their position as well as time, they keep transmitting. So then a handheld receiver, right? So you just look at a handheld receiver. What are the unknowns? The unknowns are its three-dimensional coordinates. So where of course you are assuming a 3D coordinate system of x, y, and z coordinates. So in this case, the unknowns are basically the 3D coordinates, and so you are assuming some standardized axis, and of course the difference between the time that is on the device and the ideal UTC time. So there are four unknowns. For four unknowns, we need four equations. So this is something that we know from equation theory, which means that we need data from four satellites, right? Minimum. If we have data for more than four satellites, that is fine. In that case, these estimates will become more accurate. So what is a satellite sending, right? So if I consider a satellite, so what the satellite is sending is the satellite is sending its x, y, and z coordinates and basically the current time. So what we can do is that given the fact that we are setting up an equation, we can the way the equation can be set up is that we can look at the distance. So let's say the coordinates here are x1, y1, and z1. So this is exactly what we will have. So this is the sum of the Euclidean distance. So since signals travel at the speed of light, so of course here also, depending upon the refractive index of air and so on, corrections have to be made. So let's assume we know the speed of propagation of the signal and let it be c, right? And so then we can find out the time, right? So basically we know the time over here. We know the time, the local time, right? So we can find if t minus t1 is the time it took. So that should be ideally be equal to this distance. But then again, we need to factor in the clock skew. So if you think about it, the unknowns in this equation are essentially x1, y1, and z1, right? And delta t over here. So similarly, we can set up a system of four equations and we can solve them. And at the end, what we will get is we'll get the exact coordinates of the handheld receiver and also the difference, the clock skew between the time that is on the receiver and the time that the satellites are broadcasting, which is the exact time, right? So with this, we can calculate both position as well as time. So the position again is latitude, longitude, altitude. Also, if we take multiple position readings, we can get the velocity and acceleration and definitely the clock drift. So this was initially created by the US Department of Defense. But gradually, after 1969, uh, they have been opening up the system. So in 1973, the Navstar system was developed. Then four satellites were launched. By around 2000, military level accuracy was available to all users. So this is when this GPS boom started, where basically a large number of applications, devices, everything could use GPS signals to find their accurate locations. So now, uh, of course, other than GPS, we have assisted GPS, where what we can do is that we assume that we are not interested in the altitude. So we take three mobile towers, right? And then we take a cell phone and we triangulate. Or let's say if you're interested in altitude, we can then again take four mobile towers. So all four of them will do the job of four satellites. So then we can kind of quadrangulate and find our position as well as the time difference. So in general, when I turn the location button on the phone, what is happening is assisted GPS with mobile towers. Even though some mobile phones and some tablets may have true GPS, which is where it takes the satellite signal. So the GPS constellation that was there roughly towards the beginning of the millennium had 24 satellites and six orbital planes, four satellites per plane. So basically, they were, orbiting like this at any point on Earth. You just had to have four satellites in your range, and then you just had to listen to their signals, and that would give you a precise idea of where you are. So, of course, they were not traveling in a polar or a geosynchronous orbit. It was more like somewhere in the middle, 20,200-kilometer altitude with a 55-degree inclination, right, as compared to the equator. So, the components are like this that we have discussed the 24 satellites, and the orbital period was 11 hours and 55 minutes, right, around 12 hours. So, as I said, the geosynchronous orbit where the orbital period is 24 hours, in the sense the satellite is directly above us, is roughly 36,000 kilometers from the center of the Earth. So this is here the orbital period is half of that. So one reason is that we don't want satellites to be kind of traversing too fast. Otherwise, we'll quickly lose signals. So that is the reason this was considered to be relatively safe. And also the other thing is we would not like to place the satellites in a geosynchronous orbit of 36,000 kilometers, because then the signal will become too weak, right? So the idea is that at any point of time on Earth, we wish to see or have 5 to 8 satellites in the range. So the GPS satellite vehicle has four atomic clocks, multiple batteries, solar cells. Roughly, for a GPS satellite, it doesn't need a lot of power. It's minimal. It's around 1 kilowatt, and it uses the S-band antenna for satellite control and 12 L-band antennae for user communication. So the weight is again, it's kind of a smaller satellite, 110 weight, and the wingspan is huge in the sense that it's a 38 feet wingspan with a shelf life of 10 years. So this basically ensures that our GPS satellites, more or less, are up there for a fair amount of time. Because as you can see, a lot of our modern software that includes home delivery systems, right, cars, everything, a lot of our modern electronics equipment, they are heavily reliant on GPS. So the components in any GPS device, right, will be more or less the same. It will basically be, you'll have antennae to track the signals of satellites, and then the moment you have four or more satellites, you need to set up a set of equations and then compute the current XYZ coordinates and of course the clock skew, right? So basically aircrafts, ground vehicles, ships. So these are all, incidentally, these are examples of distributed real-time systems, but you could have others as well. All of them are reliant on satellite GPS technology. Even though, given the fact that such kind of GPS is expensive, assisted GPS is becoming more popular because it is much cheaper, but it is not useful everywhere. It is only useful in geographies where there are cell phone towers. So, how does it work? So, as I have said, you measure the distance to the satellite, which is simply, the Euclidean distance. Divide that by the speed of light. All right. So, that will give you the time that it is supposed to take. So, ideally, if both the clocks are synchronized, it will be the time of receiving minus the time of sending. But given that there is some skew, you need to add the skew to it. Add or subtract doesn't matter, right? So basically, the idea over here is that every message, right? Every message has a unique pseudo-random code with it. So with that, a determination is made regarding the message and the time it took to reach the receiver. So clearly, an accurate time is key to measuring the distance. So the GPS devices themselves or the satellites themselves are quite expensive. Expensive. They have $100,000 plus atomic clocks, right? Extremely expensive atomic clocks on board. And the receiver clocks don't have to be too accurate because in our system of equations you are computing the clock skew anyway, right? So they don't have to be super accurate. And we all know in 2022 we all know the applications of GPS technology, which are not limited to location navigation, tracking, and mapping. But the idea is in any kind of a system that needs an accurate idea of the time and position, that is where GPS is used. So, internal clock synchronization, there are two ways. One is that if we trust a machine, then we can use it to broadcast its time. So, one idea, of course, could be that we use a network time server to broadcast the time to the rest of the machines. But then there are algorithms that do not require a node or a machine with a reference clock. So essentially, we average out the times of all the clocks, and that becomes the new time, right? So many algorithms are there in this space which are purely distributed. So centralized clock synchronization is the basic NTP network timer protocol idea, network time protocol idea, where a master clock just broadcasts the time to the slaves and then they set the time to be their time. So this is centralized clock synchronization, which is quite simple. The server broadcasts its time once every delta t time units. Choosing the right value, of course, is tricky in the sense if it is too small, there will be too many messages. And if it is too large, then of course, you will accumulate more of a clock drift. So this will start causing problems. So let us assume that the maximum rate of drift between any two clocks is restricted to some constant rho over here. So this is something that clock manufacturers have to, in a sense, prescribe or give out. On the basis of that, we can decide our broadcast intervals. So if they are resynchronized every delta t time units, the maximum drift of any slave clock from the master is rho times delta t. So we can figure out, how much of a drift are we willing to tolerate. On the basis of that, we can set the resynchronization interval delta t, right? So the maximum drift between any two clocks, so which basically means that we are talking of any two slave clocks. So given that each of them can drift by rho delta t units as opposed to the master, they can of course drift in different directions. One in the positive, one in the negative. So the difference between them will become 2 rho delta t units. So this is the maximum difference that can accumulate in a period of delta t between any two slave clocks, not the slave and a master, but between any two slaves. So now I'll discuss a distributed algorithm which doesn't rely on a centralized idea, but the idea is between a client and a server, right? So it could be between, between two slaves as well. But this specific example is in the case where there is one machine, a time server, that has a UTC receiver. All other machines are trying to synchronize with it. Okay. So in this case, what happens is that if you see, we have seen this formula 2 rho delta t. So what happens is every delta by 2 rho, this is small delta, not the capital delta. Every delta by 2 rho seconds, a machine will send a message to the time server asking for the current time. The time server will respond with a message which is the current value of the UTC. So let's take a look at this. We have the client, we have the time server, it sends a request. The time server processes the request and then it sends the response, right? So if the round trip time is short, whatever is the time here can be set to the time at the client, but typically the round trip time will not be that short. So what we need to do is that we need to measure, or we need to get an idea of the delay between the client and the server. So this is not hard. If you assume that the request and the response take roughly the same amount of time, then what we can do is we can assume that in this case t1 minus t0 by 2 is actually the time a message takes to come from the server or go from the server to the client. And of course, I can subtract a part of the interrupt handling time if I know exactly when the message is sent or when the timestamp is collected from this value t1 minus t0 by 2. So what is the major problem over here? So let's first take a look at the solution. So that will tell us what is the problem. So in this case, what is happening is that every client gets to know the value of the clock at the server, for the server's clock is assumed to be accurate. And furthermore, what you are also factoring in is the time that the message takes to reach from the server to the client. So with this, if let's say at T1 we get this, so what we get the time of the server, and let's say the time that the server sends is TS. So first from T1 we subtract the time, some part of the interrupt handling time, and then the time to send a message from the server back to the client. So let's say this is the time T response. So ideally speaking, this is what the server timestamp should be, right? But if that is not the case, then this number will basically give us an idea of the clock skew. So this is the amount by which we need to correct our clock, which is nothing but the clock of the client. So in this case, what the client needs to do is it needs to correct its clock. So it could either be slow or it could be fast. So if it is slow, then of course it is much easier in the sense we just move the clock forward. But if the client's clock is fast, then we can't move it backward because time cannot appear to flow backwards. So the arriving value of CUTC will be smaller than the client's current time. So the only option which is practical without making time flow backward is to gradually slow down the client clock by adding less time per tick. In the sense, let's say after 5 seconds, we don't add 5 seconds, but we add 4 seconds. So this is one way of making up without actually making time flow backwards. So the current discussion ends over here, but the discussion on clock synchronization has by no means ended. So we will discuss clock synchronization more in the next lecture.